Okay, so fine. Today we will start neural networks, and it is quite an interesting topic which will really be with you for a long time because it is like a basics where we're going to cover deep neural networks. And most of the time in universities, even in our institute, we float a separate course on deep learning. So here you will going to get introduction what are neural networks, and most of the basics are you will find there also which are applicable, right? So here so far what we have learned is regression and classification, right? And the idea was there that we have a basis functions, and we are trying to find out a linear combination of those basis functions to fit a curve in case of regression, and to find out a hyperplane in case of classification, right? In classification, what we were doing, we were just passing these W transpose X to a sigmoid function, which will just convert your which will convert your distance from a hyperplane to a probability. That's what idea was, right? So there F was a nonlinear function, right? Here also the same case applies, right? So we have those basis functions. We are having same that F function which is non-linear. The only thing that changes from there to here is like my basis functions are adaptive now, right? At first I could have a Gaussian basis function, right? So Gaussian basis functions means like this. For an example, I have some x, right? This is my x. I have two basis function Gaussian 1 and Gaussian 2, right? So if I want to change like this x, what I will do, I just feed this x to this dense, this Gaussian basis function 1, and the same x to this Gaussian basis function 2. And whatever the value I will get, v1 and v2, I just say that I have projected my x into two-dimensional space, where v1 is coming from this one basis function and v2 is coming from this basis function, right? So this is what we knew. But here, if you remember, in this Gaussian basis function, what I had my fixed parameters. So if I fix my mean here, M1 and M2, they will not going to change any time during my fitting of curve, or in case of classification, finding out a hyperplane. This M2 will not get, M1, M2 will not going to change. Even these variance parameter will not going to change. So here we in neural network, we see these things that where basis functions are also adaptive, right? We learn a parameter here. How? So this first understand the basic structure of neural network if you have not seen so far. So what we do, we have some layers here, right? So let's say in this case, I have one input layer, one is hidden layer, and the last one is output layer. So what is happening to understand it, like for to understand this, assume that you are feeding some image here. So image may be 4 by 4 pixel image in two dimension, to 4 by 4 pixel, right? So what you can do, you just flatten that image into 16 by 1 vector, right? In raster scan way. So this will come here somewhere. First row will come till here, right? Second row will come till here in vertical fashion, and then likewise. So this is like 16 by 1 vector, which you can feed as an input. So what you had a two-dimensional image. You flattened that image into one-dimensional vector, and this you feed this one-dimensional vector as an input here. You do some calculations. This is a hidden layer, and what is the structure here? That in hidden layer, just to simplify, let's say I have two nodes in a hidden layer, and I have two nodes at the input layer. It means my image was of 2 pixel only. My first pixel is x1 and second pixel is x2, right? So what I can do, I connect my x1 x2 to both these units, and to understand it intuitively, each unit is nothing but a logistic regression, right? You remember what is logistic regression? There you do W transpose X and you then sandwich it to a sigmoid function. So this was my logistic regression. So I had 2 pixel image, let's say X1, X2, X1, X2. So for logistic regression, what I have been doing, I was doing W transpose X and I was passing it to some sigmoid function, right? This is what I was doing. So W transpose X means I have W1 and W2, W1 and W2, which I am taking a dot product with X1 and X2, right? W1 and W2. I am taking a dot product with X1 and X2. So this X1 and X2 is nothing but these are the pixel here. And you take W1 here, W1, W2 just for representation purpose. What you do, you multiply this X1 with W1. Like in dot product, you multiply X1 and W1. Then you multiply X2 with W2, the X2 with W2, and then you are adding it, right? Like you do in dot product. So the input for this node will be what? It is X1 W1 plus X2 W2, right? X2 W2. And this is nothing but W transpose X. Then you are passing this into a sigmoid function. And it will convert into some probability between 0 to 1, right? So let's say I am denoting this X transpose W by A. So the sum X1 W1 plus X2 W2 is represented here as A. So everything that goes here in this node will be represented by A. And when you apply any non-linearity on it, which is sigmoid here, so then you apply non-linearity on A, you will get Z outside, right? Then this Z will propagate as a new input to the next layer, right? And you will do for every node here, right? You will do for every node here. So you can see just for intuitively, there are so many logistic regressions here. So this is first logistic regression. This is second logistic regression, and this is third logistic regression. If you are applying sigmoid function for activation, right? Then all these sigmoids will result some Z1, Z2, and Z3, right? If there are 3 nodes here. Then these Z1, Z2, Z3 will be the new input as X1, X2 was the input here. So this Z1, Z2, Z3 will be the new input for the next layer. Again, you multiply it with the next W's and feed it to the sigmoids. And whatever will come, it will be the probability. It will be again Z1 and Z2. And if it is the last layer, rather than saying it is Z1, Z2, you say it Y1, YK, right? So I'm a bit casual here in explaining the things and assuming that you have seen so many times. And if you have not understood it, you can ask me. Like for simplicity, this is like my hidden layer. This is my 2 pixel image X1, X2. I just multiply it with, there are how many weights? There are 4 weights in first layer. So W1, W2, W3, W4, right? And in the second layer, I have 2 weights, W1, W2, right? Because I need to change the, I need to uniquely show that which W I am talking about. I will subscript the layer number here. So this is layer 2, right? And this is layer 1. So my superscript is 1 here for every W. So it means I can uniquely find out which W I am talking about and in which layer, right? Any question here? So the input here will be nothing but a dot product, which is, for this case, I am getting 2 edges inside here, right? So these are 2 edges that are going inside here. So I need to multiply X1 W1 and X2 W3 as per this notation. So this is W3 weight, right? On this edge. And X2 will be multiplied by W3. So here, if you feed it, So it is x1 w1, x2 w3, right? So this is nothing but it is x1 w2 and this is x2 w4, right? You multiply x1 w3 and x2 w4 and then sum it. This is your new a. So you can say this is my a1 and you can say here it is a2 and you apply it sigmoid, then you will get z1 and z2. So is this clear to you guys? Because it is very, very important to understand the notations first. I am explaining your notations right now and the overview of like what we do in neural networks. Anybody have any confusion? Please let me know.
Sir, for the second question, the weights are also something we know beforehand, or are we using logistic regression to find them as well?
So that is like for every machine learning, the task is for every machine learning algorithm, the task is to find out W's. So I don't know what W will be. We will see like how to find out the exact W's. But right now I'm telling you the structure. So if there is any problem in understanding the structure, you please let me know. Secondly, we will see like how to find out the values of these W's. But right now I'm just explaining you like how to see my neural network notation wise, right?
Sir, in this, does every in each layer, does every node have same non-linear function or like different?
Yes, so this is the design issue, and if you just switch in, if you happen to be switching to this research fields, and you can try different nonlinear functions. For generally, what we do and what we you see there, you will find out like people try to use same nonlinearity, like sigmoid for every layer in first hidden layer, but it is not restricted. You are allowed to take any non-linearity on any node, but you should remember it because you need to back propagate it. We will see like how to back propagate those things. But it is quite flexible in general. You can take any non-linearity. For an example, in here I can take sigmoid, right? And for second node I can take 10h, right? Though 10h can be represented as sigmoid, so you are allowed to do that.
Okay, sir.
Anybody else have any question? Right? So fine. So this is like now. Okay. So if you don't have any questions here, let's go to the next slide. The functional transformation is like this. So I will just try to get. I will try to show you this thing also here. So for an example, I have some nodes. This is my layer, input layer. So this is x1, x2, and x3, right? And then you go to this. This is, let's say, my jth node, right? So I can represent my weight like this: wj1, wj2, wj3, right? So it means the first thing, the first variable here, j, will tell you where you are exactly going, right? And the second variable I will tell you what is your input, right? So wji means that I am talking about my jth node right now, and all the inputs are coming from first layer previously can be denoted by I. So it will be w1j, w2j, w3j, right? This is how you can see. So if there are d dimension, like here there are 3 dimension, I can write it as in this summation. So it will be summation w j I, and for this example, I have taken I equals to 1 to 3. I equals to 1 to 3, right? And for every layer, there is some bias also, right? So this is because this bias is for jth node. So I can write it wj0 because it so this wj0 is a bias. And which layer I am talking about, it will be denoted by this superscript. So here I am talking about my first layer. If it is second layer, then it could be second, right? Whatever goes inside this layer will be represented by A. So all these summations here, when you do, you will finally get a scalar number which is represented by A. When you apply activation on A, you will get Z, right? J will tell you that this activation is coming out from the jth node. This AJ is telling you this all these numbers are going inside that J node. After applying the nonlinearity H, which could be sigmoid or 10H. So the H is nothing but it is a nonlinear function which is known as activation function. You will get Z, right? This is how you can write it. Finally, the second layer also can be written like this. For my output layer, right? If it is a regression, I can take my output exactly as a AK, right? So I should not apply any nonlinearity if it is a regression, right? Because what nonlinearity do, let's say you are doing sigmoid, so it will sandwich between 0 to 1 number. If it is 10H, it will sandwich between -1 to another +1. But generally in regression, you want to map it from -infinity to +infinity. So here the nonlinearity function is generally taken as an identity function. So once you multiply, you sandwich, you give any function to identity function, it reverts the same number. So at the output layer, if it is regression, then there is no need of applying nonlinearity there, and it is just identity function. If it is a binary classification problem, just apply sigmoid, as we did in logistic regression, right? And for multi-class problems, we applied softmax. So softmax, what softmax do? So let's say that I have 3 nodes at the output, which is applying sigmoid. So I will get, let's say, Z1, Z2, and Z3, right? Z1, Z2, Z3. When I apply softmax, so this is nothing but it is Z1, Z2, Z3 I'm getting from sigmoid function, right? So there will be some probability which is getting 0 to 1. But I need to apply a softmax function here. What I will do, I will take e to the power Z1, right? E to the power Z2, e to the power Z3, and I will normalize it. What do you mean by normalize? I will take the sum of e to the power Z1, Z2, Z3 and normalize it. So for example, the normalized value for first layer will be e to the power Z1 upon e to the power Z1 plus e to the power Z2 plus e to the power Z3, right? There are two benefits there for this, because always we want to see everything in terms of distribution. So the first advantage for putting anything exponentially is we will get a positive number, because exponent is something like this. So exponents are something like this, right? So whatever, whether you get a negative or positive number, it will always convert it to a positive number. And doing normalization will convert it into convert into every number between 0 to 1, right? So it will actually convert my Z1, Z2, Z3 into a probability distribution where all sums to 1 and each number can be seen as a probability between 0 to 1. I hope this is clear to you, this softmax function. Yes or no? Can you write quickly, yes or no? Good. So if it is a multi-class classification problem, I will apply softmax function. So regression, it is identity. For binary classification, it is sigmoid like logistic regression, and for multi-class classification, it is softmax. So you will get lot of sigmoid functions or at the layer output layer Z1, Z2, Z3. Then you just pass them to a softmax layer. It will give you a probabilities. Right? I've sure told you what it is. So I'm just so now here onwards, I'm taking this neural network as as an example, just to discuss everything. So in this book, we call this neural network as a two-layer neural network. It doesn't count input layer because it doesn't have any parameters to modify. So this is first layer, and this is second layer, right? So this, according to this book, Christopher Buschek, PRML, this is a two-layer neural network, and I will consider whatever I will discuss from now onwards. I will take this. I will take the same structure where I have only two layers in the neural network. First layer is my hidden layer, and the second layer is my output layer. And the input layer, I specifically say that it is an input layer, right? So I specifically say this is the input layer. Then first layer is this, which is hidden layer, and then the second layer is nothing but it's output layer, right? All these weights which are shown here will be given as a superscript 1, and all those weights which will be given by superscript 2. And if you're not able to visualize the thing, so you can see if you want to write all these weights into a matrix form. So can you imagine this is what you get from Z1 to ZK, or sorry, it is other way. So it is Z1 to Zm, right? It is from Z1 to Zm. So you just make a matrix like this. In this matrix, this is your first row, this is your second row, this is your third row. Then the rows will be corresponding to the layers, to the nodes in a layer. So this will be for first node, and this will be for the last node in the hidden layer. And all the weights which are going here will come in the in this first row. Likewise, right? We will see. I will show you this just to make you a bigger picture in your head. It is like you can write this. Now, if you multiply Z1 and Z2, Z1 to Zm here, right? What exactly you are getting? You are getting these values here, A1, A2 kind of things. Because this is a dot product of this row with this vector, then this row with this vector, then this row with this vector, right? And this is nothing but A1, A2, A3 for the next layer. And if you apply again that non-linearity, it will be again Z1, Z2, Z3 for the second layer. So we'll see it. So now if you want to write what is the output value for this two-layer network. So this is your first layer, right? So this is my first layer. And I'm talking about the jth node of the first layer. So this is my first layer. This is my input layer. This is my first layer. And this is my output layer, which is nothing but second layer. So here it is showing that you are talking about the jth node, right? You are talking about the jth node and all the i's which are going into this. So this is I1, I2, I3, right? And this is nothing but it's a bias for the jth node. And this superscript is saying that I'm talking about my first layer, right? So this is my first layer. So it is what all are going inside this jth node. It is nothing but aj, right? It is nothing but aj. When you apply non-linearity here, it will be zj, right? So it is zj, right? So you will be like z1, z2, z3. And now he's talking about the kth node in the output layer. So this is the kth node in the output layer, right? This is the kth node in the output layer. So it say that all z's from 1 to m. So if there are m nodes here, right? So z1, z2, zm all will go into this, right? And you apply the bias to this node. And what you will get, and then you apply, let's say it is a binary classification problem, then you apply sigmoid to this as a nonlinearity. What you will get is nothing but zk, but because it is output layer, so you say notation wise it is yk, right? I hope this is making complete sense to you guys. Can you quickly type yes or no for this, just to understand this? Very good, very nice. Now, what I can do, I just change this, the same, just to more beautifully writing the same expression. What I can do, well, like we did in the last lectures, I can merge my bias into the same vector, putting x0 as 1, right? This is the same old trick. If I do this same thing, then I can write the same expression more concisely, right? More concisely, right? Here bias are absorbed in the same vectors. Okay, so we'll discuss it later, the skip later. So now what we are doing here is approximations. So let's try to understand the better feel of neural network. For an example, you are trying to, in case of regression, somebody is giving you these blue dots, right? So this is x1, y1, and it is xn, yn, right? So all these blue dots is a data set, right? These blue dots are a data set. So it is in a pair of xi, yi. Somebody asks you to just find it out. What is the function that can be fitted to this data set? All these, let's say there are 50 data points. These blue points are 50 points. And somebody asks you, what do you think, which curve or which is the function that can fit properly to this data set using neural network? So what you have done, you take a 3-layer neural network. In hidden layer, there are 3 nodes. At input, you take just your input x and y, right? X1, X2, let's say this is. And, or let's say this at input, it is x only. And with one bias, 1x. And output, you are predicting what is y. So what is happening for every x? For every x, you are this node is predicting this function. This second node is predicting this function. And this third node is predicting this green function, right? Then you take a linear combination pointwise of all these 3 functions, because you're multiplying each function with some constant w1, w2, w3, right? It is nothing but a linear combination of all these functions pointwise. It will give me the final function. And what is its final function? It is this function curve, right? It is its final function. So what exactly I'm trying to tell you here is that hidden layer, what it do, it extracts some features and it use these features to construct the higher level objective, right? Higher level functions. So because the first hidden layer extract some underlying pattern, this second hidden layer extracts second underlying pattern, and third hidden layer will extract third underlying pattern. And then finally, what this output layer is doing, it is just taking a linear combination of all these underlying patterns and finally composing a final output, which we need, right? And it do for everything, right? And it can construct for any function. It is not just parabola. It can approximate sinusoidal. It can approximate this absolute function, and even this square function, which is quite non-differentiable function, right? So it is just not these functions which we can see visually. Neural networks, why they are so popular? Because it can approximate any complex function, right? That is what is the hypothesis behind. The only thing is that you need to find out what is the right parameters, like how many layers is to be required, and in each layer how many hidden units should be required, right? So classification, again, there is a 2 hidden layer. There are 2 hidden layers, right? And this is input layer, And at the output layer, I need to classify whether it is 1 or 0, right? Whether it is a blue or red point. Right? So this first hidden layer, what it will do, it it is a logistic regression, let's say. So it creates a first hyperplane. The second hidden layer, it creates a second hyperplane. Then I will take a linear combination of this hyperplane, W1, W2, right? And I again apply a nonlinearity here as a sigmoid. The moment I apply a nonlinearity, it will convert into this red boundary, right? And this is the final boundary I will get, right? So intuitively here, what we are saying that it is trying to find out the underlying pattern. All your hidden units are trying to find out the underlying pattern in terms of features. So they are extracting features separately, and they collectively using all those features to finally make the decision, right? Uh, just a minute, guys. Hello. Okay, fine. So is this clear to you guys?
Yes, sir.
Intuitively, the sense is like all the hidden units are trying to find out some patterns, and these patterns are then collectively making a decision, right? And if there are more than one hidden layer, so this is how they do. First hidden layer is, let's say I'm trying to find out whether it is a car or not. So I just, as an input layer, I give one image. So first hidden layer is trying to extract whether there is a tires or what are the structure. First hidden layer is find out tires. The other hidden layer, the other unit is trying to find out what is the body, right? And so this hidden layer is trying to construct what is the final form of this body and tires, right? And finally it says, yes, this is a car, right? So you can go to any level. So you can keep on adding these hidden layers, 1, 2, 3, 4, and the idea is to to mine these features which can construct the higher level features, and then finally collectively taking a decision. Okay. The cost, this is the first model which you are studying in this course, where the error function is not convex. It means you have learned this logistic regression, then you have learned this linear regression. All those functions were convex, and it means there was a global minimum. But for this function in neural network, they are quite non-convex in nature, right? And what this non-convexity do, the problem with this is that you can have many solutions, because there's no algorithm so far in optimization theory that can, in this scenario, that can give you this local minima, right? If you start from here, you just block here, and if you start here, you block here, right? So therefore we don't talk global minimas. We always say that we want to find out a local minima. Local minima means which is with the minima that is available in the nearest neighborhood, right? In neural network, there are so many minimas available. This is how it look like egg tray kind of thing. And if you start from anywhere, you will just get to the nearest local minima. But it is not a problem here. Why? Because most of the minimas are actually giving you the same accuracy. Why? So there could be so many weight vectors which will give you the same accuracy. I'm not saying the best accuracy, but these many vectors will give you the same accuracy. There is a difference between same and best, right? Why it is so? Let's say I have a hidden layer. In this hidden layer, I have two nodes, right? So if I'm using tan-h function, so the tan-h function, what it do? So I feed some two edges here and one output edge there. If I multiply all things with negative both side, right? Nothing will going to change in respect of tan-h, right? So at first, when I had not multiplied anything with negative, I got, let's say here, Z1. And if I multiply everything with negative, now again I will get Z1. So nothing will change effectively, right? It is because of this is tan-h is an odd function, right? So it means the vector which you could have like this. So let's say this way. So now you get W1, W2, W3, W4. This is my weight vector for this layer, right? I can still get the same accuracy if I get minus W1, minus W2. I can still get the same accuracy if I get the minus W3, minus W4, right? Even this way, even this way. So there are how many ways? If there are two hidden units, it means there are 2 to the power 2 hidden ways, right? So if there are m hidden units, there are 2 to the power m different ways I can construct the weight vector, which will give me the same accuracy, right? This m factorial is coming because now if I have this neural network, this is my hidden layer H1, this is my hidden first unit H1, and this is my second unit hidden layer H2, right? And the weights are going like this: W1, W2, W3, W4. So I have this H2 and H1. So it is W3, W4 now. It is H2. And it is H1. Still effectively in terms of neural network, isomorphically nothing has been changed. And my weight vector is being changed now. First it was W1, W2, W3, W4, right? It was W1, W3, W4. Now it is W3, W4, W3, W4, W1 and W2, right? So how many ways I can arrange these? In a m factorial ways I can arrange it. It means total, the without changing anything, I can construct my weight vector if I am having m hidden units in m factorial into 2 to the power m ways, right? So if you start from anywhere, there is a high possibility that you might get a different weight vector, but still you will get the same accuracy, right? So no need to worry too much about like what is your initial point here. Though the more you discover, the more you find out like what are the better ways to do it. So sir, this question is this valid for 10H? When it is taken as activation? No, it is true for another activation functions. There is a research paper which is written here. You can just refer to the book, and but it is mentioned that other than 10H also you can find out the same ways to construct the things, right? Okay. Now the best part comes which like you are good at it. You know how to find out a likelihood function. Here the assumption is that I am at the output layer, right? Let's say I'm doing a regression. So I am at the output layer, right? Or I'm at the output layer. So this output layer will give me some number, right? So I am approximating, let's say, some sinusoidal or some parabola like this I have just shown you here. So whatever the number I get from this output layer is, I will take it as a mean the same way, right? I take it as a mean and I say that there is a variance around it, right? It can go up and down with some variance. So my function which I am projecting, which I am trying to find it out, is nothing but it's a mean with some noise. I'm just trying to find out some probabilistic view to see this thing, right? Though here, if you remember, I have just find it out like this. This is my function, square wave. But here I am seeing this square wave as a mean function, like we have done in linear regression. And there is a probability that I can go away from this mean is this a beta inverse, right? Like this is a then the likelihood of generating T is always high if it is at the mean, right? So I want to maximize it. And I will do it for everything. So what I can do, I just multiply all those probabilities. And this is known as likelihood function, right? If I take a negative log of it, it is nothing but I want to minimize it. When I take a negative log of it, this is what I get. But I want to maximize it with respect to, can you tell me quickly? I want to maximize this likelihood function with respect to
W.
W. Same old story, right? And so this is constant. This is constant with respect to W. I left with this, right? I left with this. And when I maximize it, I will get nothing but it is a sum of square error which I am minimizing, right? So whatever my prediction, how far it is from the true. So this is like I'm just taking a sum of square error. And here I am showing you that sum of square error minimizing is nothing but maximizing likelihood of function, assuming that you have a Gaussian distribution at the output, right? So you will find it out this a W using stochastic gradient descent function, like we did in logistic regression. Once you get a W, this W is nothing but a maximum likelihood estimation. You feed this W and find out the variance, right? So this is just a probabilistic view. Generally, you don't need to do this. You just need to do this only, right? To train a neural network, assuming that your variance is constant and you don't care too much about it and you always want to predict a mean. So in case, then you just minimize this sum of square error function, right? So I hope this is for today. It is fine. We will continue tomorrow. If you have any question, please let me know. Otherwise, you can ask me question tomorrow at the beginning of the class. Thank you very much. Drop your attendance.